Okay, hello everyone. Thanks for coming in. My name is Hyunseung Hwang from Korea, and today I'll be presenting our work, SHAP-based explanations are sensitive to feature representation. This is a joint work with New York University, and I will touch on something that the overall SHAP explainability field hasn't covered yet. Okay, let me start with a simple question. Can we trust explainers? Now, suppose a loan applicant named Anne is rejected for a loan. The explainer tells us that age is the most important feature in our decision. But what if the story can change, even when the model and the prediction stays the same? Now, before we dive more into the example, just for a quick refresher, SHAP is a local explanation method. It tells us which features are the most important for a specific prediction, like a rejected loan. It's local, additive, and widely used to explain black box models. If we look at the example plot below, SHAP generates a score for each feature and adds up to the prediction. But our concern is how robust is this explanation? Now let's go back to Anne. If we look at the training data, Anne is 30 years old and is the only one who got their loan rejected. Now Anne is unusually young in the training data and SHAP picks up on that. Now worried, the bank tweaks how age is represented. Instead of using the raw number, they bucketize it into two buckets, one under 50 and the other 50 and over. Now the importance of age drops, while the relative importance of education goes up. Now the bank can say that the age was not the most important feature. The prediction does not change, nor the model, but the story completely shifted. Now this is not a hypothetical trick. Here is an example of a SHAP plot where the ranks have shifted from feature manipulation. With the original model and the explainer on the left, age was the most important feature. But after the new representation that is fed to the explainer, age drops from the most important to the fifth important feature. Note that even the plot on the right, the SHAP values add up to the same number that is that of the one in the left. We seek to answer two main questions in our work. Are SHAP values stable under innocuous feature engineering? And can we manipulate explanations without retraining the entire model? Unlike many works on robustness of explainability techniques, we do not retrain the model, nor we change the type of the explainer SHAP. If you look at the pipeline below, the model is trained with raw data, but we apply feature engineering just to the individuals who are being explained. So the next question is what is this innocuous feature engineering? Just like how the bank represented age into two groups, we can represent continuous features by dividing them into multiple buckets. One common way to divide a continuous feature like age is to divide into groups of 10. In the figure below is an example of dividing age into 4 buckets where the minimum value is 20 and the maximum is 50. We will call dividing data into equally sized buckets equi-width method. And one thing to note is that we are free to move around these red boundaries as much as we want. So then, if we can move them around, how do we find the boundaries that minimize the importance of a sensitive attribute? We use Bayesian optimization. Given a fixed number of buckets, we can choose the bucket boundaries that minimize the importance of age rankings. So like in below, before we had bucket boundaries in 30 and 40, we moved them to the left. Now we have a different set of buckets that can reduce the importance of age. Here is a simple overview of the experimental setup of our work. We use two real-world data sets, ACS income and public coverage. And for the model, we use XGBoost that is trained with grid search, about 7,000 searches. And for sensitive attributes, we try different types of features. First is a continuous feature age that I will be focusing on this presentation. But in our paper, we also have a section where we bucketize categorical features like race. For bucketization, we generate 2 or more buckets with equal width or Bayesian optimization that we talked about in the previous slides. Now, to evaluate the explanation differences, we use 2 metrics. First, fidelity. That tells us how well the explanation predicts the outcome. Note that when we shift the representation of the data, it can sum up to a different value than the original explanation that was produced with the original SHAP. And second, we use ranking shift. We measure how much does the ranking of the sensitive feature shift after we apply bucketization. Let's take a look at the general bucketization of age. On the y-axis, we show the average ranking of feature age across all test samples in 5-fold cross-validation. Note that we are applying the same bucketization on all the data that is being explained. So if we personalize attacks by generating bucket boundaries for each individual, the rankings can shift a lot more. So in the y-axis, we can see that the lower the value or the rank means that age was considered more important by SHAP. The error bars represents the standard deviation of across the folds, showing how consistent the rankings are. Let's first look at the blue graphs, the equi-width bucketization. Except when only using 2 bins, it fails to lower the importance of age compared to the original representation. In some cases, it even makes them more important. In contrast, when we use Bayesian optimization to choose the bucket boundaries, we are able to consistently demote the ranking of age. Importantly, during this optimization, we ensure that the fidelity of the explanation, or how well it predicts the model's output, is at least as good as the equi-width counterpart. In other words, we preserve the predictive quality of the explanation while strategically reducing the importance of sensitive feature like age. We show that even subtle changes in pre-processing to the explainer can be used to manipulate feature attributions and explanations without changing the model at all. Now, the key takeaway is we cannot assume that SHAP explanations are the ground truth. Explanations can shift subtly under feature transformations, so we need tools to measure explained stability and to detect potential manipulation. To conclude, SHAP-based explanations are sensitive to feature representation even without touching the model at all. This raises important concerns about fairness, reliability, and accountability in explainable AI. Thank you for coming, and feel free to ask any questions.